So good morning, everybody. Thank you very much for joining us this morning. And thanks very much for Anjana for joining us today. She'll be the star of the show, and I'll introduce Anjana more formally later on. But today we'll have two speakers. Anjana will be the second speaker. We'll talk about what the IPCC report says about drought. And I'll precede that with just a brief introduction to the broader IPCC report, just touch on a few of the key points that the report makes. But prior to doing that, I'd like to begin on behalf of USQ to acknowledge the traditional owners on the land on which we gather, and we'd also like to pay our respects to elders past, present, and emerging. I'll now try and share my screen. And by the way, we'll open up after Anjana speaks. After I've spoken, Anjana speaks, then we'll have a Q&A session, so you can just ask questions using the audio function. Can you hear me okay? Yep, great, thanks. And can you see the slideshow? Yeah. Okay, so I'd like to give a brief overview of the IPCC AR6 2021 report that came out a couple of months ago. And this report focused on physical climate science. And I'd like to acknowledge the fact that most of what I'll show obviously comes from that report, but I'm also going to draw upon information in two previous special reports, one on the ocean and the cryosphere, and another one on a report on global warming of 1.5 degrees Celsius, and also draw some information from the Bureau of Meteorology website. I think the first point to make is this report is extremely impressive. It's a magnificent piece of work. It was written by 234 authors from 65 different countries, and they assessed 14,000 scientific publications and synthesized all of the information that's contained in those, relevant information that's contained in those publications. They also addressed, so they read and altered the report or responded to the comments, 78,000, more than 78,000 comments. That's a huge amount of work. And finally, when the SPM, the Summary for Policymakers, was produced, 46 different countries commented on the Summary for Policymakers, and that was taken into account by the scientists, but the document is the scientist's report. So it's an independent assessment of the science, and the IPCC is widely regarded as the foremost authority on the science of climate change in the world. So let's begin by summarising some of what's in the report by looking at what it says about the past. And just to kickstart things, I took this slide from the Bureau of Meteorology website. So this shows global average temperature anomalies from 1850 through to near present. And no surprises to anyone online that you can see that there's lots of year-to-year decadal generational variability. There's also been this underlying trend to higher temperatures. But let's now let's now look at what's the cause of that warming. And in order to address that question, scientists around the world from many, many different centres use climate models that are mathematical models that encapsulate the dominant processes that drive the Earth's climate system. And here you see some equations that are used for the ocean, and there are many, many other equations for the atmosphere, equations for land surface processes, cryosphere, and interactions between those various components. So they're magnificent achievements in human history, I think. The ability to simulate and use these climate models to project what's going to happen next, but also importantly, to try and explain what's already happened. And that's what scientists have done, and that's what the IPCC report covers, one of the many issues. But the big surprise to many of you is that the models do an absolutely terrible job in simulating the observed temperature if you only force them with natural processes. So if you only force these climate models from around the world with natural processes like solar variability and volcanic eruptions, then you get the green band, whereas the observed changes are given by that black time series. However, if you then force exactly the same models, not just with natural processes, but also anthropogenic or human factors, then you do a very good job in simulating the observed temperature change that's occurred. So the models do not capture the accelerated warming that's occurred over the last 70 years if you only force them with natural processes. Another thing we might ask ourselves is, how unusual is the temperatures we're seeing now relative to what we've seen in the past? Well, obviously, relative to the 19th century, the temperatures we're seeing now are much higher. But can we go back further in time? And the answer is, thanks to some magnificent work done by paleoclimate scientists, we can compare the temperatures we've witnessed in recent times with the temperatures that were experienced over the globe using paleoclimatic information to provide a proxy for global temperature change. So this is fantastic work that's getting better and better every year. And so let's have a look at, so what I've done is I've squeezed this bureau plot into this tiny little plot here, but it's the same, roughly the same information from 1850 to 2020 from multiple observational estimates. So you can see there's a little bit of scatter, but they all show very marked warming over that period. So let's now compare that with the temperature estimates for the last 2,000 years. And if we do that, we don't get anything because it's not working. We get that. So you can see that the temperatures we've experienced in recent times is the highest it's been. The planet, it's the warmest the planet's been for at least 2,000 years. So you're living in historic times. The other thing that the IPCC report does is estimate the contribution of human activity to the amount of warming that we've seen. And this is the observed change in temperature from over the recent 20-year period relative to the latter half of the 19th century, so 1850 to 1900. And the world's best estimate of that warming is this, 1.1 degrees Celsius with a small error bar. The report then goes on and says, well, what has human activity done to global temperature? And the largest bar there is the contribution from greenhouse gases. So it warmed the planet by about 1.5 degrees Celsius. However, at the same time, we've also been polluting the atmosphere with aerosols, and that helps to cool the planet. So when you combine these two together, the large reddy pink bar with the aqua bar, you end up with this third bar on the left. So that's the net impact of human activity on global average temperature. And what's the answer? 1.1 degrees Celsius. How does that compare to the observed change? Virtually identical. So the conclusion is that the observed temperature change is almost entirely driven by human activity over that period, from the latter half of the 19th century to near present. And the report goes on to conclude that it is indisputable that human activities are causing climate change, making extreme climate events, including heat waves, heavy rainfall, and droughts, as we'll see from Anjana's talk soon, more frequent and more severe. And it also concludes that recent changes in the climate are widespread, rapid, and intensifying, and unprecedented in thousands of years. And we saw a little bit of that just then. And finally, climate change is already affecting every region on Earth in multiple ways. So these statements are stronger than previous statements. So that's the past and present. But what about the future? Again, we can use these magnificent tools, climate models. Magnificent, they're not perfect, let's face it, but the best tools we have available to project what's going to happen in the future. And so we can provide projections for the future, but we need scenarios of what greenhouse gases and other factors are going to be doing over coming decades and over the coming century. So what will happen is a strong function of what the world decides to do with its greenhouse gas emissions. And so, not surprisingly, the global temperature change we're going to experience over the coming century is a strong function of those sorts of scenarios, the scenarios we have for greenhouse gas emissions. And so with scenarios that have very large greenhouse gas emissions coming ahead, then you get very large temperature change, up to and beyond 5 degrees Celsius relative to the reference period. On the other hand, if the Paris Agreement is successful, then we may end up down near the bottom where you get that aqua one, where the warming is well below 2 degrees Celsius relative to that reference period. So it's also interesting to look at the global, that was the global temperature change. What does the spatial pattern of that warming look like? And you can see that whether the global warming is 1.5 degrees Celsius on the left, or 2 degrees Celsius in the middle, or 4.0 degrees Celsius on the right, global average warming, the patterns of warming look very similar. They're not identical, but they're very similar. And so you can see, for example, that let's look at the 4 degree warming one on the right. You can see that the warming is greatest over the Arctic. The warming over land and over much of is greater than over the ocean. Warming over Antarctica and parts of the Southern Ocean tend to be warmer than the global average. And if you look carefully at Australia, you can see that the warming tends to be greater over the interior than it does near the coast, than it is near the coast. Other projections include what might happen to September Arctic sea ice area. So how much sea ice do you have, the aerial coverage in the Arctic during September? So that's, just at the end of summer up there. And you can see that no matter which scenario you choose, the amount of ice you have during September is projected to be, on average, much less than what it was during the latter half of the 20th century. And it makes a difference if you reduce emissions, but it still doesn't stop the projections from being much lower than the recent values. The other thing the model makes clear is that global warming, and not surprisingly, increases the frequency and intensity of heat extremes. So this is a really interesting plot. If you look at those little dots, what it shows is how frequent you get a 1 in 10 year event. So for the reference period, 1850 to 1900, you've got 1 dot. So that gives you a feel of how often it occurs. But then in the present climate, that risk of getting that same temperature value or exceeding it is now 2.8 times greater. If you get 1.5 degrees Celsius, then it'll be 4.1 times greater. 2 degrees Celsius will be 5.6 times greater, and 4 degrees Celsius global warming, then the chance of getting that what was a 1 in 10 year event is 9.4 times more likely. And similarly, if you look at the bars down the bottom, the 1 in 10 year event is already 1.2 degrees warmer than it used to be over land. Under 1.5 degrees Celsius, it'll be 1.9 degrees warmer. Under global warming of 2 degrees Celsius, it'll be 2.6 degrees warmer. And under 4 degrees Celsius global warming, the 1 in 10 year event will be 5.1 degrees Celsius on average over land. And remember that interior of Australia warms more than land overall, and so that value would be greater for the interior of Australia. And it's not that surprising to see these numbers, because if you have a distribution of temperatures, for example, in a current climate or a past climate depicted by the black curve, so you can see that you've got a small chance of getting very high numbers, you've got a small chance of getting very low numbers. If you then apply warming and that distribution moves to the right, you can see that the likelihood of getting some extreme, what was an extreme value depicted by that dash bar, and it's also given by the area under the graph to the right of that dashed line. You can see that, yes, that area is still small for this example, but it's much, 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 much larger than it was in the old climate. And of course, the values, the equivalent value here too, is now somewhere up here. So it's just a simple way of understanding why you get these changes in the frequency and intensity of extreme events. And a somewhat similar story applies to heavy precipitation over land. Previously, we saw that long-term average changes, you can get, we'll see that next, I think. You can get, there's expected to be an increase in both the intensity and the frequency of intense rainfall events. And so the report concludes that, an important conclusion of the report is that to limit global warming, to avoid some of these worst scenarios, sustained reductions in carbon dioxide, methane and other greenhouse gases are necessary. This would not only reduce the consequences of climate change, but a good side effect would be, or co-benefit I should say, is to improve air quality through reducing some of those pollutants. And they also conclude that unless there are immediate, rapid and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees Celsius will be beyond reach. And some of you might think, oh, what's the big deal about 1.5, 1.6, 1.7? Does it really matter? And the answer is yes, it does matter. Every single 0.1 degrees Celsius matters. So we know from the previous IPCC reports that, for example, something close to home for most Queenslanders, the Great Barrier Reef, which is a warm water coral, those reports concluded the following: that the majority of warmer water coral reefs that exist, 70 to 90% of them, will largely disappear when global warming exceeds 1.5 degrees Celsius. And the authors concluded that statement they made with very high confidence. They also stated that reef restoration options may be ineffective if warming exceeds 1.5 degrees Celsius. So this is an instance where, yes, climate change adaptation is very important, can help a lot, but there are limits to how much adaptation can do. And for coral reefs, it seems that adaptation, the global warming above 1.5 degrees will take it beyond our ability, or the coral's ability, to adapt. And finally, the species and diversity of remaining reef communities are projected to differ from present-day reefs. That again is said with very high confidence. So in other words, we're going from a beautiful biodiverse system that we currently have to something that's much less diverse and to be frank, from an economic point of view, much less attractive for tourists. The other thing that matters is projected is large sea level rise, and again, it depends upon the scenario we use for greenhouse gas emissions. But importantly, the report points out that these are likely ranges. So it's not the full range of what might happen. And so what they did here was to just highlight one possibility that cannot be ruled out, is that there are aspects of the climate system, the stability of the ice sheets, for example, that aren't as well known as we would like them to be known. And there's strong evidence now suggesting that this instability may have already begun, and it would be irreversible on a millennia timescales. And the report provides an indication of the sort of sea level rise that might occur if that instability, subject to that instability process. And you can see that it's much higher than the other likely ranges. So there's a great deal of more clarity in this report, but there's also some really troubling things that we don't know enough about, and it needs to be factored in when we consider what might happen in the future. So it's a low probability event, but it's not a zero probability event, and it's a high, very high impact event. And the other reason why we might bother to try and keep things to 1.5 degrees Celsius or close to it is because we've made an international agreement. Australia has joined in this agreement, as have virtually every other country in the world. And that's the Paris Agreement, which says that we should keep global temperature rise this century well below 2 degrees Celsius above pre-industrial levels, and to pursue efforts to limit the temperature increase even further to 1.5 degrees Celsius. So we're obliged to international processes to try and keep global warming to those levels. So thank you very much for listening to that introduction. And now what I'd like to do is to more formally introduce Anjana Devanand. So Anjana received her PhD from the Indian Institute of Technology, Bombay, India in 2020 for her research on the influence of land processes on the Indian monsoon. So you might have something to talk about with Hannah, Anjana. She has also worked in the United States and Australia on understanding changes in regional climate and its impacts. And currently she's a research associate at the ARC Centre of Excellence at UNSW in Sydney, which is where I got my PhD from, working on regional simulations of drought. So thank you very much, Anjana, for joining us today.
Yeah.
Would you like to share your screen?
Yeah. Can you see my slides?
Yep.
Thank you, Scott and Crystal, for having me here today. Good morning all. So I'm going to talk about the drought information in the latest IPCC report that Scott introduced. So these are the contents of the report. So this report is from the working group 1 of the IPCC, which talks about the physical science basis of climate. There are 3 types of chapters in the report. So chapters 2 to 4 talk about large scale information about the current state of climate, the varying influence on it, and as well as future projections. Then chapter 5 to 9 is a process understanding kind of chapters that look at various global cycles and how they are influenced by different processes. And chapters 10 to 12 are regionally focused chapters, which talk about the current state of climate, the attribution to human-induced warming, as well as future projections. So the drought information in this report that I'm going to be talking about today comes mainly from 3 chapters. Chapter 8, which is about the changes in water cycle. It contains information about some global perspectives of changes in drought. And chapter 11, which is a regional chapter that talks about weather and climate extremes, including drought. And chapter 12, which is intended to be a link between this report and the working group 2 report, which will come out early next year. That will be looking at the impact of climate change on various sectors. So I'll be going through the key points about drought from these 3 chapters in the report. Before going into the drought information, some quick terminologies. So the report uses multiple evidence that is available. So it can be observations, theory, or model simulations. And the authors assess the type and quality of evidence and the agreement between them to assign some confidence levels to statements. So for example, we saw that findings related to, say, the global temperature rise would have a very high confidence, whereas other changes that are related to other aspects of climate need not. So I'll be talking about the confidence level of various drought information from the report. In addition, the regional information in the report is presented for various reference land and oceanic regions. So over Australia, we'll be looking at the northern, central, southern, and eastern Australia, the 4 AR6 regions that are used by the report. Now, projections of climate into the 21st century are specified with respect to some baseline climate. So you saw the pre-industrial climate 1850 to 1900 that was used to specify the levels of increase in global mean temperature. So this is the primary baseline that's used in the report. In some cases, they also use a modern baseline from 1995 to 2014. Now going into drought. So drought is a deficit in moisture, and there are different types of drought depending on where this moisture deficit exists within the Earth system. So a lack of precipitation, which is called a meteorological drought. Most droughts start with a lack of precipitation. It then propagates to different parts of the natural and managed systems. So, and the droughts can last from few weeks to a decade or more in time scale. It can lead to lack of stream flow or lack of water storage in surface water and groundwater systems, which are known as hydrological droughts. It has impacts on water quality as well as water supply. In addition, the lack of precipitation can lead to a deficit in water that is stored in the soil moisture, causing water stress for plants, both crops as well as natural vegetation, causing agricultural and ecological droughts. So the effect of precipitation on drought is easy to understand because it affects the water input into these various stores and leads to various types of droughts. But other climate drivers like radiation, temperature, wind, and humidity also affects drought because it affects the amount of evaporative demand of an ambient atmosphere. So the section numbers, so this number 8.2.3.3, I'm adding the section numbers from the report so that you can go back later and maybe look for more information about these points there. So droughts are affected by increases in atmospheric evaporative demand. So that means that even if there are no precipitation changes, a warmer atmosphere can hold more moisture. So that means that a warmer atmosphere has more capacity to dry out a land surface. So an increasing atmospheric demand can increase the severity of droughts, even in the absence of a precipitation change. In addition, changing circulation patterns that change the weather anomalies that bring rainfall to a region can also affect droughts. In a warming climate, the changes in atmospheric evaporative demand, or AED, is a main driver of drought. The report states this with high confidence. In addition, there are other factors that affect drought severity. The first one is plants. So it is understood that there will be an increase in the water use efficiency of plants under high carbon dioxide concentrations. So plants are expected to use less water with increasing atmospheric concentration of CO2. But at the same time, there is expected to be more plant growth, which will ultimately use up more of the water from the soil and dry out the land surface. So currently there is low confidence on which of these processes dominate. So we don't quite fully understand how plants affect the severity of droughts. In addition, human activities and decision making related to the use and management of land and water also affects the severity of particularly agricultural, ecological, and hydrological droughts. Moving on to a large-scale perspective of drought, this is from chapter 8 of the report. So the report states that in observed changes, the frequency and severity of droughts has increased in some regions with high confidence. These regions are Mediterranean, Western North America, and Southwestern Australia, and they attribute this to human-induced warming. In the case of projected changes, there is high confidence that soil moisture will decline in semi-arid winter rainfall dominated areas. So this includes some of the regions where they already report observed changes, as well as some additional regions like the Amazon basin, Central America, and Southern Australia. These regions are expected to become drier both due to reduction in rainfall as well as the increase in evaporative demand. So to assess regional droughts in chapter 11, we saw that there are different types of droughts. So the report used various types of indices to assess the changes in each of these types of droughts. They use precipitation deficits to assess meteorological droughts, changes in atmospheric evaporative demand, soil moisture, as well as indices that combine AED and precipitation to assess agricultural and ecological droughts. And they use stream flow or runoff to assess hydrological droughts. Looking at the observed trend in droughts. So the figure which I've taken from chapter 11 of the report shows the historical linear trends in 3 indices of drought. Without going into details of what these indices are, the first 2 indices are representative of meteorological droughts, and the last one is an index of agricultural and ecological droughts. And the brown shades in the figure indicate an increase in drought conditions. So looking at meteorological drought, you can see that there are some increases in few regions in Africa and South America. In the case of agricultural and ecological droughts, you can see more brown shades than the first 2 panels. So there are stronger signals than in meteorological drought because it includes the effect of AED in addition to precipitation changes. There are increases in several regions in all continents and decrease only in one region, which is Northern Australia. Coming to hydrological droughts, which is not shown in this figure, but it's more frequent in fewer regions than agricultural and ecological droughts. Mediterranean is one region where there is high confidence in more frequent hydrological droughts. And we see that the report also states that there is medium confidence of increase in Southern Australia. The report looks at model evaluations of drought simulations from multiple studies and assigns some confidence level as well as points to some areas where models are deficit in terms of drought simulations. So meteorological droughts show disagreements compared to observations, and there is large spread between the models. The spatial pattern of AED simulated by the models are reported to resemble observations, but there is again strong divergence between models, both globally and regionally. There are some deficiencies in the simulation of soil moisture. So the soil moisture is reported to dry out too quickly in the summer. So there is some evidence that the models may be over simulating the intensity of droughts. And there are biases in the projected magnitude of droughts, which could be related to these biases. In addition, so there is a storage of carbon dioxide, carbon in the land surface vegetation, and the sensitivity of this carbon storage to changes in soil moisture is also uncertain between the models. So at catchment scales, the hydrological models that are used to assess the changes in runoff, there is a lot of uncertainty in the hydrological models as well. Overall, the report states that there is medium confidence in the overall performance of models for assessing droughts. It is the consideration of multi-model projections which increase this confidence. The report assigns low confidence to assessments based on single models. Coming to detection and attribution of droughts. So there is medium confidence that human-induced climate change has contributed to meteorological droughts in 2 regions. There are human-induced warming contributions to single meteorological events or sub-regional trends in other regions as well, which I haven't listed here. Anthropogenic forcings have contributed to soil moisture deficits and atmospheric-based drought indices due to the effect of AED. And there is medium confidence that human-induced climate change has contributed to increasing trends in agricultural and ecological droughts in some regions, including Western North America and the Mediterranean. The hydrological deficits are more difficult to assess. So there are some studies that attribute hydrological deficits to human-induced climate change, but the use and management of water for human activities are also a major influencer for hydrological droughts. Coming to projections of drought, so the strongest increases in drought frequency and intensity are visible in the case of agricultural and ecological drought. So the figure that I show here is from chapter 11 of the report, and it shows the changes in soil moisture relative to the pre-industrial baseline. The first panel is changes in drought intensity, and the second panel is drought frequency. You can see that the x-axis is for different levels of mean global warming, and the changes are for regions that we have at least medium confidence of drying trends, which are shown in panel C. So you can see that it includes regions in Western North America, Central North America, the Amazon, Western South America, Mediterranean, Southern Australia, and South and East Australia. So there are increases in drought. There are projected to be increases in drought intensity and frequency for each additional degree of warming in these regions. For projected changes in other types of drought, for meteorological droughts, several regions display frequent droughts in warming, but the projected changes are overall less extended than for the agricultural and ecological droughts that we saw on the previous slide. So projected changes in agricultural and ecological droughts are strongly affected by AED in a warming climate. There are some uncertainties that are related to the water use efficiency of plants and how it can compensate for the increase in droughts. In addition, the influence of the global land carbon sink under low warming scenarios is also an area of uncertainty for agricultural and ecological droughts. For hydrological drought, on average, the global runoff shows wetting tendencies under warming, but there are deficits in low flows in large regions. There are a few studies that attribute the increase in hydrological drought to human-induced warming, but human water use and land surface changes are also highly important. So, and these show up in the projected uncertainties as well. Coming to regional drought for Australia, for these 4 regions. So I'll be talking about, this is from chapter 12 of the report, and it summarizes the information of observed and projected changes in aridity, hydrological drought, and agricultural and ecological drought for these 4 regions. In the case of aridity, there is observed decrease in precipitation during the cool season with medium confidence, and its aridity is projected to increase for both southern and eastern Australia. In case of hydrological drought, there is observed increase in southeast and southwest areas of southern Australian region, and future projections show hydrological drought increases for warming levels of 2 degrees Celsius or higher with medium confidence. In the case of agricultural and ecological drought, there are projected to be increases in southern Australia and eastern Australia. In observations, there is already an increase in the southern Australian region and decrease in northern Australia. So with this, I've summarized the information up to chapter 12 of the report. In addition, there is an Atlas chapter that provides an assessment of changes in mean climate at regional scales. And there is also an interactive web page that we can use for exploration of datasets. So I've created some plots to showcase how we may use this information. So here we see changes in annual total precipitation from 3 different datasets created using the Atlas. The left panel is using the previous version of the coupled model intercomparison project, the high emission scenario. The central panel is the current version of CMIP. Again for a high emission scenario into the far future, and the right panel is the regional simulations over Codex Australasia. We can see that there are projected declines in annual total precipitation over southwestern Australia, consistent with the increase in aridity that is projected by the report in this region. This atlas can also be used to make regional plots for assessments. So here I show an index of meteorological drought for southern Australian land region. You can see that there is a lot of interannual variability in these projections, but there are some slight declining trends as well, which is potentially contributing to the medium confidence decline that is projected for this region. So that's it from my side. Thank you.